Hello and welcome. Today, we are putting on our detective hats to solve a really cool chemical puzzle. This one is taken directly from a university chemistry exam, specifically question 5. So let's see if we can crack it. Okay, let's get right into it. Here are our 3 suspects for today's case. Now, I know these chemical formulas can look a little intimidating at first glance, but don't worry. We're going to break them down and figure out exactly what's going on here together. So here's our game plan, our case file, if you will. First, we'll get to know our chemical suspects. Then we'll crack their secret electron codes. After that, we'll put them in a magnetic lineup to see how they behave, uncover a surprising partnership, and even expose a master of disguise. All right, let's start with the basics. First step in any investigation. Who, or in this case, what are we actually looking at?
All 3 of our suspects are what chemists call complex ions. The easiest way to think about them is like a little solar system. You've got a central metal atom, that's your sun, and orbiting around it are these other molecules or ions called ligands. They're all bonded together as one unit.
Okay, now for the first major clue in our investigation. You see, each of these complex ions has a unique electron configuration. Think of it like a chemical fingerprint or a secret code that tells us almost everything about its identity and behavior. And what is an electron configuration really? Well, in simple terms, it's just the rulebook that tells us exactly how all the electrons are arranged in their different energy levels, or kind of like their designated rooms around that central metal atom. Now here's where the real detective work begins. Just like in a real case file, sometimes the clues you get, even in an exam question, can have typos or mistakes. So our job isn't just to take the evidence at face value, but to figure out the story that makes the most chemical sense. So this is the scene of the crime. We have our 3 suspects on the left and the 3 electron codes found on the right. But right now, they're all mixed up. So the big question is, how do we correctly match each suspect to its code? Let's start with the manganese complex. We see the central metal ion is manganese with a +2 charge. That means it has 5 important electrons in its outer shell. Now, this complex is what we call high spin, which is just a fancy way of saying it likes to spread its electrons out, keeping them unpaired. So, 5 unpaired electrons. And if you look at our codes, bingo, the configuration T2G3 EG2 describes exactly that. 1 match down. Now, we can use that same logic for the others. The nickel complex has 8 of these d electrons, which lines up perfectly with the E4T24 code. But this leaves the cobalt ion with the last code. And wait a second, the numbers don't add up. This is where that misleading clue comes in. For the math to work, we have to assume there was a typo in the original question, and that it's actually cobalt 2+, not 3+. If we make that correction, it's a perfect match. A classic detective move, finding the logical fit even when the evidence is a little off. All right, now that we've correctly identified our suspects, it's time to see how they behave out in the world. We're going to put them in a lineup, a magnetic lineup. The key property we're testing here is called paramagnetism, and all it really means is that materials with unpaired electrons are weakly attracted to magnets. Here's the important part. The more unpaired electrons an ion has, the more magnetic it's going to be. So the process here is actually pretty simple. All we have to do is look at the electron codes we already figured out and just count up the unpaired electrons for each ion. That number will tell us everything we need to know about its magnetic strength. And when we do the count, the results are crystal clear. Our cobalt complex has just 1 unpaired electron, the nickel complex has 2, and then there's manganese with a whopping 5 unpaired electrons. This gives us a really obvious lineup. As you can see, the manganese complex isn't just a little more magnetic, it is by far the most magnetic suspect of the bunch. It's in a league of its own. Now, these ions don't usually hang out by themselves. They're always looking to form connections. So let's see what happens when our most magnetic suspect, that manganese complex, decides to partner up with someone. Our manganese complex has a -2 charge, so it's on the lookout for a partner with a positive charge. And a perfect candidate is the calcium ion, which has a +2 charge. It's like chemical Lego. Opposites attract, and these positive and negative pieces are going to click together perfectly. So the +2 from the calcium and the -2 from our complex ion balance each other out completely. They form a stable, neutral compound with this clean, simple formula. You could say it's a clean getaway. But hold on, we're not done yet. There is one final fascinating twist in this case. It turns out one of our suspects, the cobalt complex, is a true master of disguise. This phenomenon is known as isomerism. It means you can have molecules that are built from the exact same atoms, the same chemical formula, but those atoms are arranged differently in space. It's like having the same set of Lego bricks, but building two completely different things. So let's look at disguise number 1. In this form, all 4 of those NO2 ligands connect to the central cobalt atom through their nitrogen atom. This specific arrangement is called the nitro form. Pretty straightforward. But here's the trick. That same ligand can actually flip itself around and connect through one of its oxygen atoms instead. So in disguise number 2, one of the 4 has done exactly that. It's created a nitrito link. And even though the parts are the same, the shape is different. It's a totally new isomer. So there we have it. We've matched the codes, ranked the suspects, and even uncovered a shapeshifter. Case closed, right? But you might be wondering, why does any of this matter outside of a chemistry exam? Well, the truth is, these complex ions are incredibly important. That electron structure we just decoded, it's responsible for the brilliant, vibrant colors you see in paints and stained glass. They also act as catalysts, speeding up chemical reactions that are vital for industry. And maybe most importantly, their unique structures are key to their function in medicine. For example, some platinum-based drugs have a specific square shape that allows them to bind perfectly to the DNA of cancer cells, stopping them from dividing. It's amazing stuff. Cracking this one puzzle from one exam question just goes to show you there is this incredible, hidden world of structure and function all around us, in everything we see and touch. And it's all just waiting for the next curious detective to come along and start asking questions. Thanks so much for watching.